That's okay. Right, fine. All right, welcome everyone to another in-person AI/ML seminar, and everyone on Zoom as well. Yeah, I'm really excited to have Robin Gia visiting us. He recently joined USC as an assistant professor in computer science. He's already got a budding group from what I hear. He's done a lot of really cool stuff. Many of you might have seen his early work on robustness, but he's been sort of thinking a lot about evaluation, a lot about building really robust and reliable systems. And today we're going to hear a lot of stuff about evaluation. He's also received paper awards and a bunch of things. So yeah, we love reading his paper. So I'm really excited to have him here. Right, let's welcome Robin.
Yeah, thank you very much, Samir, and thank you all for having me and for coming out to this talk. Yeah, I guess I just wanted to have a quick note. So this talk will be like entirely stuff that is still in progress right now. We're kind of like trying to target UMNLP with the stuff I'll talk about today. But there's definitely still work to be done. Hopefully you find this interesting. I remember when I went to my first like ACL conference, I like thought that people would talk like workshops, people would talk about like work in progress. And then I realized that wasn't really the case, but maybe this is an attempt to do that and share what's going on before it goes public. And selfishly, hopefully, this is my chance to test out whether you buy some of these ideas that we're working on. Okay, so like Samir said, we're thinking a lot about outer distribution evaluation. I want to start by just thinking a little bit about like why do we need outer distribution evaluation, right? So, okay, there we go. Okay, so I like starting with some of these news headlines that I think capture what can go wrong when you don't evaluate critically. So back in 2018, right? So maybe there's definitely been a lot of news since then, but even in 2018, there are these claims, for example, that we have an AI that can read a document and answer questions about it as well as a human. There was an article in the USA Today that says robots are better at reading than humans. And okay, let's take these claims at face value for a while, right? So can machines actually read? I will argue, and I think people in the room here know the answer is no, not really. They can do some impressive things. This is true. Like, so here's one way to test this out. I can go to Google, I can type in a question, and it can tell me what the answer is often. So I ask, who was the King of England during the American Revolution? It retrieves this passage that tells me the correct answer, King George III. But it turns out I can start making Google give me wrong answers. It's the exact same format of question. I've just replaced England with Portugal, and I get told that it's John VI, who is clearly the wrong answer because he became king in 1816. And if we look a bit more into what's happening, apparently he was the king during some other revolution in a different country. So there's some like shallow keyword matching here, but this is not really like reading, right? Nobody would read this passage and conclude that he was the king of Portugal during the American Revolution. By the way, I tested this recently in Google. You'll get a different one box if you Google this, I think today, but it'll still say the same answer. Here's another example. I can ask who was the king of Italy. I get told it was someone who was the king during World War I and World War II. Okay, so, and we'll see more examples, and I'm sure many of you in your own research have these examples of things not really doing reading. Okay, but the question I want to build towards is like, where did this idea come from, right? How did we end up in this world where we had these articles saying that robots can read as well as humans? In the particular story I was giving, this actually came from one specific data set, which is SQUAD, this question answering data set out of Stanford. And it is true that on the SQUAD leaderboard today, like models are like 4 points better than human performance. So by this metric, yes, robots are better at reading than humans. And it's not necessarily trivial to like fix these benchmarks to be kind of challenging to models in the appropriate ways. In fact, some of the work I did during my PhD, we tried to fix SQUAD and have like a newer version. This also turns out to, at this point in time, models can do very well on them. And this is true, you know, for things beyond question answering, right? If you look at Glue, or even if you look at Superglue, we're at this point where the human baselines are somehow like below the best models. And what that says to me is that there's really like two big problems we have in our field, right? On one hand, we do have all these like kind of engineering problems, basically like how do we actually build models that can do these very general tasks, or that can actually read passages, that can actually understand language, some strong sense of word understand. And then we also have measurement problems, right? Because the like things we're doing to measure progress are kind of telling us the wrong answer, right? They're telling us that we've achieved much more than we actually have. So today I'm going to talk, actually maybe roughly like the first two sections will be more focused on the sort of measurement aspect. And then I will come back to some other things about kind of how do we actually make models better in some specific ways for out of distribution settings. But the first work I want to talk about is work from my PhD student, Amir Gabole, and this is on a way to create benchmarks that measure generalization to the long tail. And just kind of, I wanted to say quickly before we go further, feel free to interrupt me at any point with questions, and also stop like at the end of each section for questions. Okay, but for now, let's get started here. So in this project, we've really been trying to think about like benchmarking methodology, you can say. So what is a benchmark? A benchmark is something where you can feed it some sort of method, right? Whether that method is like some sort of modeling method, like fine-tuning BERT is a method, right? Or something like I'm going to ask humans to tell me whether what the right answer is on these examples. These go into a benchmark, and the benchmark basically gives you a score, right? How accurate did this method do on the benchmark? So when I say benchmarking methodology, we're thinking about like, okay, how do we construct these benchmarks from some pool of existing examples, right? And so the kind of baseline strategy that you're all familiar with is called random trained test splits, right? So baseline, you just like take your big pool of examples, you just randomly split them in a trained test, and then you say accuracy on the test set after you've trained on the trained set, that's the score we're going to assign models. And the problem, as we kind of already saw from things like squat and glue, right? Those are all essentially i.i.d. splits, and these tend to overestimate model abilities, right? Like in practice, it's really like not ever going to be the case, right? That your trained set exactly is drawn from the same distribution as your test set. And so like, how do we come up with a better alternative to this approach? I think before we can even think about like coming up with a better alternative, what we need to figure out is like, what do we even want in like a benchmarking method, right? What are the desiderata here? And I'm going to propose a few of them, and we're going to try to make progress on these. So some things that seem good, like I argued, I think we believe that they should be more challenging than random splits, because we believe random splits are overestimating accuracy. At the same time, we don't want them to be like impossible, right? So I can create some sort of impossible trained test split if I just put like things that are like very, very different category of examples in test than trained, right? So there should be some sense in which like learning from the training data should make it possible to do well on the test set. It's hard to really get specific about exactly how you show this, but we can have some intuition maybe. Hopefully these are somewhat motivated by actual shifts that occur in practice, right? Like what are the actual sorts of differences between train and test that we need models to be able to handle well. Another thing that's maybe not obvious at first, but I think is important, is that we don't want this to be adversarial to any particular model, right? We kind of want to be able to fairly compare different models. That's what these benchmarks are used for, right? Comparing different modeling methods. And so we don't want something to kind of arbitrarily penalize one modeling approach at the expense of others. And finally, we want something that kind of broadly applies to a lot of different tasks that we might want to use, right? So random train test splits are really good at this. Like you can do that literally for any data set you have, right? Can we come up with something that's close to that level in terms of being easy to apply? So with all these sort of desiderata in mind, our proposal here is, instead of doing random splits, can we create a train test split where the test set requires you to be able to generalize to kind of tail examples or things that are like less common? Yes, Samir.
So is this methodology for just creating the benchmark, which is sort of separate from train test split, which is sort of defining what the model is being trained on also.
Well, the train test split defines what the model is being trained.
But you could imagine creating the benchmark separate from what you trained. So are you thinking of benchmark as a train test split, or are you thinking of benchmark as just creating the test?
Yeah, I guess I'm thinking of a benchmark as consisting of a train set and a test set, and I guess like an evaluation metric or something, which we're kind of not doing anything new with here. I guess that aligns with stuff like glue or squat, right? Because there's like a standard training set that's kind of defines the rules of the game. Because yeah.
I guess something that I would have expected to see in Adversarial, which I'm curious if you can comment on. I think behind what you're trying to get at here is that there is some true test set that you actually care about, which is not well captured by your i.i.d. data. And what you want, the thing that you want is that my evaluation metric correlates with performance on this true test set in some sense. Would you agree with this?
Yeah, that's interesting. We think about this. Yeah, I guess I think the way we've been thinking about it is kind of in terms of like, there's some like skills that you might want the model to have, like for example, like being able to handle rare words, like something like that. Because I think I don't know, I guess I'm not sure what maybe I'm not sure there exists a perfect test set in the first place. And so I don't know how to even think about correlating with that. Yeah. So yeah, I guess we've been thinking more along the lines of like, there's certain like generalization challenges. So things like, yeah, rare words, or maybe like generalizing to longer examples or generalizing to unseen semantic parse templates or something. Like these are sorts of like skills that you want the model to have. And can we make sure those skills the models have those skills? Cool. Okay. So some other just kind of like quick inspiration, this concept of kind of like long tail distributions in language, I think comes up quite a lot. And just one example is that you may be familiar with this idea of this like Zipfian distribution for the lexicon. Basically, there's this very like heavy tail distribution of words, like individually are like quite unlikely, but together they correspond to kind of a significant fraction of words that occur, right? And because there's this very heavy tail, you can't really expect the training data to kind of like exhaustively cover everything that's in the tail, right? And so that's why we really think you need some sort of other skills to generalize to all these rare phenomena. On the other hand, if you look at what happens in actual data sets oftentimes for like reasonable reasons will tend to sample the head. So just a couple snippets. HopIQA, one data set where they explicitly say, oh, we're going to choose popular pages from Wikipedia. Natural questions, which is a data set based on Google queries. So they try to make sure that you have like questions that were asked by multiple users in a short period of time. And you can kind of see the intuition here for why you would want to do that. You want to get things that are like kind of, the more you might think if you're going to collect a data set, you might as well start with the things that are like things that many users ask. That makes sense. On the other hand, this means you underrepresent all of the sort of tailish queries. And this is not even to mention kind of some less obvious stuff, such as the fact that when you crowdsource data sets, right, crowd workers are like often trying to like think of off the top of their head something to write. And this is, I think, also likely to be like very common or come from a much more narrow distribution than like than what you might actually want to capture. Okay, so back to like, what are we actually doing? How are we going to measure this long tail generalization? The big idea really is to use language models, because that's the hammer we have these days. So we're just going to start with some big set of examples, and I'm just going to assign each example a score with a language model. And importantly, the score is only going to depend on the input, right? So if we're doing, let's say, semantic parsing, this only depends on the utterance. It doesn't depend on like the logical form at all. So we're just looking at like what, in terms of the natural language, seems like more common or less common language. Once we do that, we're just going to do the split where we put high likelihood examples in the train set and low likelihood examples in the test set. And then we evaluate models on these train test splits. Okay, so so why do I think this is a good idea? So if we go back to our kind of desiderata, I basically had these like 5 summarized here, these 5 bullet points that we wanted. The question of whether it's challenging is kind of more empirical, so we'll get back to that one. I think for the other ones, I'll present some arguments. Some of these are less airtight than others, but I think there's some intuition here. In terms of being possible to do well, I think this is really hard to actually like definitively prove unless you have some very well-constrained, maybe synthetic environment. But I think one reason to expect this to be possible is that there's no like big domain shift happening, right? So I think some other times when you test generalization, you have like a completely different way that you collected data between training time and test time. You have completely different, like you train on Wikipedia and test on news or something, right? Here, it's like we're starting from a single pool of examples that was all kind of collected in the same way from the same place. And so there's no sort of this extreme domain shift. There's no obvious sort of like big extrapolative leap that we are requiring models to do. In terms of practical motivation, we really kind of talked about this idea that like the tail of the distributions kind of fundamentally like can't be covered by our training data. This thing about not adversarial, this goes back to what I said, where because we're not conditioning on the output, we're only looking at the inputs when we're scoring this. We're not like the actual prediction task doesn't show up at all in how we define these splits, right? So we're not being adversarial against any predictor. You might, of course, also think that even if we're not doing that, it might wind up being adversarial, but we can measure that. We'll come back to this in a bit. And finally, this idea about broad applicability, I think this is one of the nice things where basically anything where you have like textual inputs, you can run this, right? You just like have, you apply a language model to this data. And this also lets you get away with not actually creating like a separate challenge data set, where you just reuse some of the existing data as your challenging test set. Okay. Cool. Okay.
So just understand the method, you're putting a hard threshold, you're sorting it and just cutting it off at some.
Yeah, that's what, well, I'll describe a variant. That's like the basic version, yes. Yeah.
Strong separation between
Yeah.
And like, is it empirically verified that it is possible to do well based on that training set? So some models.
Right. Yeah. So that's. Oh, sorry. Yes. So the question was about this thing about possible to do well, and I kind of agree that this is not. I don't think we have like a super strong case here about whether it's really possible to do well. And I think the question was also like, do we have some way of empirically measuring this? Yeah, I think that's pretty challenging. Like there's been some work that I know about where you can work in some sort of like, yeah, some sort of synthetic domain. And then you can say like, oh, you know, there's some model that's like doing the task optimally, in that it's just like inferring what all these different like logical operations mean or something. And then you can reason about whether it's possible to do well or not. Here, yeah, here I think we don't have a strong argument. I guess perhaps all we can say is that there are some of the things that at least make me skeptical that some other splits are possible to do well on are like not present. So I mentioned domain shift. Actually, another big one is I think oftentimes you just like train on one data set and test on another. There's also the fact that like the annotation protocols are usually different, right? So it's like not even clear that it's really the same task often. So we can avoid stuff like that. Yeah.
To extend this, like not just saying any model, is it even possible to have any training set which preserves the separation you take, like the high probability one going to your test set? Is it possible to have a training set which satisfies that like, criteria and still and in a model that at least even if that is not possible, I don't know how we can take.
So I think it's, well, one thing to think about is like, I think it's possible in the sense that like for a human annotator, like you could give instructions, like usually when you give instructions, you can show like some head examples, and they should still be able to do the more tailish examples. Well, you would think maybe. I guess we haven't actually verified this. We do know that, like, this is foreshadowing, but we do know that the examples in the tail are not necessarily ones that are like more ambiguous to human annotators. Yeah. So that's what I would say, right? So basically, if I guess more generally, like, as long as the head of the distribution like gives some actual language understander enough information to know what the task is, they should be able to take that knowledge and apply it to the tail. Right? So in that sense, it should be possible. Yeah. Okay. Okay, let's keep going. So just a little bit more detail about what this procedure actually looks like. So there's basically a couple of things that are left underspecified. So number one is like, where exactly do these likelihood scores come from? So you have a couple options here. So one thing that we tried is to do this like prompting thing. So this is nice because you don't have to do any training. So we can take GPT-2 and a data set specific prompt. So for example, for Spider, which is this like SQL semantic parsing data set, we just have a prompt that's like, write a database question, and then the utterance, and then you score how likely that is. For SNLI, we can do this thing where we thought it made sense to try to match kind of how SNLI was actually constructed, which is that their annotators were given a premise and then they wrote a hypothesis. So we can basically have the premise as part of the prompt and then score how likely this hypothesis is given the premise. So this is kind of more lightweight, and this is maybe closer to like what is rarer in like the pre-training corpus distribution. Another thing you could do is you could do fine tuning, and this is maybe going to get closer to like what is rare within the pool of data that you have. And so you can basically do the same thing, but then you can also fine tune GPT-2 with this like sort of cross validation structure, right? So you break it up into K folds, and then you train on K-1 folds and score the remaining K fold, and you do this K times, and you get scores for everything. Okay, so these are some options for getting likelihood scores. I think in general, they seem pretty similar in terms of the overall trends. Okay, so the other thing, this goes back a little bit to Samir's question about like exactly what is the splits. So yeah, so the basic split is literally just like split on likelihood, like I said. There's one thing you might be worried about, which is that likelihood correlates a lot with length. So like sentences that are longer just will have low likelihood because you have to generate more words correctly. And so we have the second option, which he called as like length buckets, or I'll describe it as like minus length, like controlling for length. And basically all we do here is we bin all the examples within, for a given length, we bin those examples and we just do the partition within each bin. And so this guarantees that, yeah, like the distribution of lengths is matched between training and test. Okay. So on to the actual numbers here. So first we'll talk about Spider. So on the slide we have, so the first, okay, so what's going on in this table? So we had two different semantic parsing models here. You can either train T5 to do semantic parsing, you can also train GPT-2 to do semantic parsing. And you can see on the top, on the random split, they're doing whatever between 78 and 69. On the bottom, we have R splits, right? You can see that R splits are indeed quite a bit harder, both the likelihood ones and the ones where we control for length. These are both the fine-tuned variants I'm showing here. In the kind of middle rows in white, we're just showing that for semantic parsing, there's been, I guess, quite a lot of prior work actually thinking about other possible ways you could split the data. So for example, you could do it so that like kind of program templates or like some program templates are only seen at test time, not training time. Or you can do this thing called based on TMCD, which is basically saying that like certain compounds in the logical form, like certain pairs of things co-occurring in the logical form should only co-occur at test time. You're testing how well you can handle these sort of unseen compounds. And our splits are kind of similarly hard. I wouldn't say that there's like necessarily the hardest method is the best method here. but I guess it's sort of comparable to these things that are testing, like one very specific challenge and like maximally trying to get that one specific challenge. The other thing I want to point out here is that it doesn't seem like we've particularly like been adversarial to GPT-2, right? So GPT-2 was also what we used to score the likelihood. And for both T5 and GPT-2, there's like a 12-point drop between random and the likelihood splits, right? So it doesn't seem like we're unfair to GPT. Okay, so I think a big question that we are still trying to understand is like, why are these splits harder? And basically the answer seems to be that there's like a bunch of things going on. So we already talked about length, that partially, generalizing from shorter to longer sentences is a challenge. But again, even if you control for that, our likelihood splits are still harder. There's a thing I mentioned about compound divergence. And this is, again, seems to be partially there in the sense that we have like, there's more disparity in terms of what compounds occur at train and test for our splits compared to like a random split, but it's much lower than this TMCD split, which is like optimizing for that metric. And so this also doesn't seem to explain really everything about it. We had some analysis of like rare words, and that also is like a partial thing. So in this plot, so the big histograms are, we took basically a bunch of different random splits of the data, and we counted like what fraction of the words in the test set are like rare. For rare, we just did set some threshold based on like frequency in Google Books. And you can see that there's a few, and then we also have these individual points for like the splits we get from other methods. And you can see in particular the two triangles on the right correspond to the two different versions of the likelihood split. And so we do have like more rare words in the test set than you would expect from like the average random split. On the other hand, like the effect size isn't like that great. It goes from like 2.4% to like 2.9% or something like this. So there's like a slight enrichment of rare words, but that also doesn't seem to be the whole story. So I think that like my take on this right now is like, I think it's nice that we seem to be having just like many different sort of challenges present at the same time. And the hypothesis maybe is that because of this, hopefully it's harder to kind of overfit a method to this benchmark compared to if you had something that was like focusing exclusively on length generalization, right? There might be kind of one trick that you can do to get length generalization and suddenly you're doing much, much better. This seems to be more realistic in that there is a lot more different things happening at the same time. Yeah, Samir.
Maybe you get to this later, but there is only a certain level of generalization you can test just by doing the train test split given the same tool. So going back to your first slide or whatever, you're talking about squad.
Yeah.
Do you think if you had applied this to squad, things would be different and your test performance would be worse than humans for the models that you have today?
That's a good question. I think it's possible. Like honestly, I've done some error analysis on squad. Sorry, the question was about like you're fundamentally limited in what's present in the data with this method. So like, for example, if we did this for squad, would we see a large drop in performance? And so you're absolutely right that we are limited by what's present in the data. Yeah, based on when I looked at squad before, like I actually do get the feeling that there is some like interesting stuff. Like I remember just doing some error analysis. Like there are some examples that are like consistently hard for methods at the top of the leaderboard. And there is some like interesting stuff going on there. There's also a lot of noise, but yeah, I think it's not obvious one way or the other, but I definitely think it's possible that you could get kind of get some drops. And yeah, maybe the next slide will also get at this because we also did SNLI, which is a data set you might think is also like very simple. And an SNLI, this also makes splits that are quite a bit harder, right? So you go from like 90% accuracy for like Roberta Bayes, you go from like 90 accuracy to like 81% accuracy. Yeah, so this is like a nice proof of concept that this works more than just semantic parsing. Yeah, and even on data sets that you might think are pretty easy. And the last kind of result I want to show related to SNLI is there's been work on like adversarial splits or something that also make harder test sets, but they will also seem to amplify the noise that was present in the data. What we've seen is that the like low likelihood examples are not necessarily those that have more disagreements in the annotation. So basically, this plot is showing that we kind of have different levels of annotator agreement across the x-axis. And then on the y-axis, we're plotting like these like likelihood scores. And there's not really an obvious like difference, right, between for each label. There's not really a clear difference in the distribution, right? If anything, it seems like there's more tailish stuff just happening at the far right, where there's like the highest annotator response. I think that's just because there's more of those examples, period. So yeah, we don't really target ambiguous examples here. Okay, so this is actually all I want to say here. And yeah, I think the point really for me is like, you know, this like status quo that we've had for a long time with like matched train and test sets really overestimates model performance. And maybe for a while that was still like, we could still make a lot of interesting progress here. But I think now we need to think a lot more about like what actually makes like a benchmark, like a training and test set challenge meaningful. And we have at least one proposal here to do it, which I think gets at some natural sense of generalization and is convenient and that you don't have to collect new data for it. Yeah, so happy to take more questions here before. Yeah.
Okay. You must have looked at a bunch of this data. I have very little intuition for like what's the instance that's all the way to the right versus what's the instance that's all the way to the left. So do you have any sort of qualitative like what is actually the difference between the highest likelihood and the lowest likelihood?
Yeah, it's like, yeah, honestly, yeah, I should have a better answer for you. I think that's something we need to do more of. Like we looked at some of those things, like I mentioned, like rare words, and it's like there's like a small effect. Yeah, honestly, it's been a while since I looked at the exact. It's a good question.
I have
Yeah.
a bunch of hypotheses and give negative when you show your results, but I'm still trying to see like what they.
Yeah. I don't think on grammaticality, like from what I remember, I don't think they looked like all that different, which is kind of part of the like mysterious part of this. I can go check again because I think also like the exact details of how we're splitting have changed since I last looked at these. Yeah, but we should look at it more. Yeah, the grammaticality thing is interesting. We looked at some. I think we looked at some stuff related to like reading difficulty scores or something. I don't think that was like a significant difference. Yeah, I don't know. We should probably just look at more examples.
I guess, yeah. Was there bias in terms of classes for SNLI?
Oh yeah, right. So that's something I left out. So in terms of, yes, there is, in terms of SNLI, there is bias in terms of classes. And so we artificially fix that by like forcing the classes to be balanced. So we split within each class. Yeah.
The neutral was in.
Yeah, I guess you can even see it here. So it's like entailment, I guess. Yeah, so entailments are just like more likely, which makes sense because they're like the most related to the premise. And then it seems like the other two are pretty similar. Yes.
So just so to make sure I understand, the idea being that hopefully it's not just separating out the complicated words. Hopefully it's not just, separating out what is grammatical and what is not. Like ideally it would be doing something where the tail contains questions like the King of Portugal during the American Revolution, which would be, according to us, like a weird question. That's at least intuitively what the hope is that's.
Yes. Yeah. That's yes. For Zoom. Yeah. So like part of the hope, linking back to the intro, yeah, part of the hope is like things like who's the King of Portugal, those sorts of questions would be like rarer and hopefully captured in this tail of the distribution. Yeah. Okay. Cool. Yeah, let's move on. And I guess we might, I'm happy to stay past to fair questions. Okay, so the second project I want to talk about also relates to evaluation, and we're looking specifically at vision and language models. So this is work with Bill Zhu and Jesse Thomason, USC. So one starting point I want to say, so I've been talking about how we need to evaluate on auto distribution sets, but there's like something that's been bothering me, I guess, which is that there are these results showing that like empirically, if you just take a bunch of models and you measure their in distribution accuracy and out of distribution accuracy, they're like quite correlated with each other. And so this is one particular paper that showed this with question answering. So they collected variants of squad on different domains. And yeah, they basically tested a lot of squad models on these. Yeah, and basically there is this pretty strong correlation here, right? And so this basically might suggest to you that like, oh, actually, if we just try to build models that optimize for in-distribution accuracy, maybe that's not that bad because that will also push up outer distribution accuracy, right? And so I think in order to really like argue for the value of OOD evaluation, we want to say like, no, there are actually situations where we can provide different guidance on modeling choices than what you would get from just doing the in-distribution evaluation. So we were kind of looking at this in the context of vision and language tasks, which is a place where there are kind of two very different paradigms that are being explored right now. So on the one hand, you can have these sort of end-to-end pre-trained models. So this is more similar to, I guess, the big language models, but now you also have an image as part of the input, feed it all through a big transformer, get an answer. But then there are also these like neurosymbolic systems. So things that try to, parse an image into some sort of like scene graph-like representation, and then maybe you do semantic parsing on the language, and then you execute the program on the scene graph, right? This is seems at least to be a very different style of system. And so we basically wanted to ask like, okay, what are actually the big differences in terms of generalization behavior for these two classes of systems? So we've been looking at a couple different vision and language tasks, but actually the one I'll focus on is COVER, which Matt was part of. So this is a multi-image data set. And so we have things like there is at least one image with exactly two dark bottles on the counter here, right? So there's like, you have to do some reasoning across multiple images, and then also like within each image, you have to also do some reasoning. Okay, and like we said, so there are two ways to do this. So maybe I'll just go very quickly through this. So basically, yeah, you can do this with a pre-trained model. There's some details about how you actually get Vigilbert to do this, which I'm going to skip through. And then there's also a neurosymbolic model where we're just going to take the programs that were for cover, the programs that were used in the cover data set. We can train T5 as a semantic parser to try to generate these programs. We can separately run a scene graph parser to generate these scene graphs. And then so the scene graphs look like this. You get relationships between objects. And then you execute these. So we have some like code that actually just like executes the program on the on the scene graph and arrives at the answer. Okay, so I think the big question is kind of like, what is like, how are the generalization behaviors going to differ? And I think there's arguments kind of in both directions. So there's the argument that like the neurosymbolic system should be like more robust. And a lot of this comes from the fact that, oh, we have these symbolic representations and it seems like they should provide strong inductive bias. And also there's just the fact like we have invested a lot of like engineering effort here, right? There's like this like executor that's doing a lot of heavy lifting in terms of understanding, being able to do counting and so forth. And there's another thing which you could see as an advantage, which is that we basically decoupled the interpretation of the images from the interpretation of the language. So maybe it's harder to latch on to kind of like spurious correlations that include both of them. But there's,
is there more supervision also for the new ones?
Yeah, there's more supervision. Yeah, because you have the programs. Yeah. Yeah. So these are all reasons like, yes, this is not, I think we're not necessarily saying that this is like a fully fair comparison, but I guess you can still see the difference between like, what does the in-distribution evaluation show and what does the out-of-distribution evaluation show? Okay, yeah. On the other hand, I guess one thing you might worry about is like, we're still relying on some sort of like neural model, right? It's not a end-to-end vision language model. We still have this neural semantic parser that we're kind of hoping is able to do some sort of, is going to be robust. And, there's various work saying that, it's not clear that these things will generalize very compositionally. There's also issues like you get error propagation in the neurosymbolic approach, because like if you have errors in scene graph parsing, you just like can't necessarily fix them. Okay, so I think this is like the kind of the arguments for both sides. And now we're just going to show kind of like some a few ways we came up with to evaluate and see what actually happens. Yes.
At least in NSP come out, I think it had shown better population generalization of down. So is there some work which is showing that NSP like neurosymbolic model is not.
I guess I'm just saying that like in terms of so you're right that like the some of the like VQA work on especially on things like Clever have shown that pretty good results. I guess Clever is pretty synthetic, I guess, is kind of part of the issue. We are I guess the other thing is that system is also different. We actually kind of want to evaluate something like that as well, but that system is also kind of different from what we have here, which is this like strict. It's not, we're not actually using NSVQA. We're just doing this thing where we like we actually just like train T5 as a semantic parser. And so so like work in the NLP community, I guess it's like like semantic parsers aren't like perfect in terms of how well they can generalize. And okay. Let me see. Okay, so in terms of how we're evaluating, let's see. So we have one idea we had that applies to these multi-image settings is to do what we were calling this like segment combined test. So basically, this is the whole idea on the right-hand side. If you have these original images and you have some question like how many images contain exactly two people or two men, well, this is equivalent to just like taking each of these images in isolation and combining them, pairing them with like a couple like random background images, or if we just use like other random images from the data set, which are like very unlikely to also like contribute to the count. And you can feed each of these individually to the model and just like get the answer and then add them all up at the end, right? These should be like exactly the same. And we can see whether models are like kind of consistent across these. So we have like, you can do these things where you're adding, you can also do these things where you're like verifying, like there's at least one image that satisfies some constraints, right? This is just you do an or at the end. Okay, so here are some results for some of these particular question types. So if you just look at the original test examples, it seems like the like end-to-end system is like doing better, right, than the neurosymbolic approach. But basically, if you then do this segment combined test, like the ordering flips, right? So like somehow VisualBERT was like getting the right answer, but it seems to be bad at counting or something, or like perhaps also like it's not used to having these like random images show up as opposed to like the like closer negatives that are actually in the data set. Something along these lines is messing it up. Meanwhile, the neurosymbolic system is like basically maintaining the exact same level of accuracy. And if you look under the hood, what's going on here is that the semantic parser is actually being very successful here. Basically, all of the errors come from scene graph parsing errors. So if you like give the neurosymbolic system gold scene graphs instead of having to generate them, it's like very close to 100%. And similarly, if you just measure the accuracy, the semantic parsing accuracy in terms of can you generate the right program, we're also very close to 100%. And so basically what this means is like it's identifying exactly the right program to execute. And when in the cases where the scene graphs were correct, right, all of these like operations where you like add in other random images, like they don't change the fact that you got the correct semantic parse and you got those particular images parsed correctly, and so you can still do very well, right? So this is I'm sorry, this is not like I don't think it's obvious that the neurosymbolic system should do this. It's only because the semantic parser is actually doing a very good job that you don't run into like spurious errors in the segment combined setting.
I guess that's probably because cover has synthetically generated text,
Yeah.
and so it's just inverting the mapping from program to text, which is relatively simple.
Like the observation is pretrained, which means that the semantic parser is able to do complex.
Apparently, yeah, in this setting, yeah.
Seems like the threat will not.
Yeah, no, that's yeah, I think that is a fair point. And I think we've been talking a lot about trying to get this also, get something like this on something like NLBR2 where you have more like, yeah, not template generated stuff. Yeah.
And I mean, that number says we probably didn't do a good enough job with cover. Like that, that's what I read.
Possibly, yeah. I can see there even there.
Do you have, I mean, I know this is a different question, but do you have any idea for visual bird? If semantic parsing is the problem, or
Yeah, that's a good question. Yeah,
if we had
we've
instead of the reference given it the gold programs, would the
give it the
performance,
gold programs. Yeah, how do you give it the gold program?
like instead of the utterance, instead of sending?
Oh, I see. So you train it to map the program plus
Yeah.
the, oh, that's interesting. So the for the folks at home, so the suggestion was like, we can train Visual BERT to take in the program plus the images and up with the correct answer. And so that should tell us whether it's like failing at semantic parsing or failing at, I guess it could be failing at execution or at scene graph generation because it doesn't have an executor built in. But yeah, that's an interesting idea. Yeah, I think we've thought about that question about like, yeah, can we understand better? Can we decompose the errors that Visual BERT is making? But we like hadn't come up with a good way to answer that question. Yeah. Do you have something to add?
Yeah, I thought somebody was trying to say that whether the semantic parser is actually going well or not. It's just that this maybe I misunderstood them. If not, but then I just want to say it's just that this data set maybe not like we didn't do a strong enough compositional split, but there has been enough work previously with images present as well, which have shown that semantic parsers, it's a program generated, the semantic parser that fails, and then we could look into its job fine. The semantic parser is the one that fails. Here maybe we didn't do strong enough.
I see. Which works are you?
Like when closure and stuff had come out, and they were when closure had come out,
Okay.
or some other work. I have to that papers, but it was a program generator that was speaking. Like
I see.
Okay. With NMS, Mac was on. Tried on closure with the program generator.
I see. Okay. Yeah. I think we do want to. Yeah, I think we should take a closer look at that. Yeah. For sure.
So here that works, it was surprising to me, but it might be.
Yeah, makes sense. Okay. Cool. Let's see. Just try to figure out how to do the user rating. Okay, we also had some results on these contrast sets, and I'll just give you the headline. The headline here is that, so you can do contrast sets where you either like perturb something and it stays the same meaning, or you perturb something and it changes the meaning. And essentially Visual BERT is like quite good whenever you just do a paraphrase, but very bad when you do something that alters the meaning. For example, changing like at least to less than is like a complete opposite, right? And so in these situations, Visual BERT is essentially has this big like overstability issue. And we can see it here that like basically on the top left, the error analysis basically like almost all the time it's just like outputting the same answer as what it output for the original version of the question, whether or not that's the correct or wrong thing to do. In the majority of cases, it's the wrong thing to do because its original prediction was right the majority of the time. Yeah, so yeah, let's see. Maybe in the time I'll try to just like very quickly mention the the last thing as well, and then we can loop back and take a few more questions. Yeah, so I think that basically, I think hopefully the interesting thing for me from this project, right, was that like, okay, we do actually have these things where there's a bunch of different tests, and they all seem to tell a similar story, which is that, yeah, these models are having very different generalization behaviors. And I think this underscores that, like, if we're trying to actually compare models that are very different, then we do need to include these sorts of non-i.i.d evaluations. Okay, very quickly, a little bit about like how to actually make models do better at something. One thing I've been looked at in the past and also now is this like idea of selective prediction. So basically, like, you know, when models can do classification tasks well, that's great, but sometimes they're going to get it wrong. And how do you have the model kind of signal, somehow realize that, oh, this is a hard example for me, and I need to abstain. And in particular, in classification, one way this can happen is if you get it input for which like none of the classes is actually relevant. So here, there's a question classification task where we've kind of removed the label for like numerical questions, and you feed it a numerical question. The model just like thinks it's actually very confident that it's a location-based question, which is entirely wrong. So you really need to abstain in settings like this, right? Because there's literally no class that's correct. There's nothing the model could do to get this example correct. The kind of obvious thing you can try is this thing called max prob, where you just like look at the confidence, the probability distribution output by the model, and you look at whatever it's like, basically use that as a measure of how confident it is. This, however, like there's cases where the model is like overconfident in this like wrong answer. And so you really want to bring it closer to this like ideal, which is like as close to uniform prediction as possible. And how do we do that? Our intuition, I think, that maybe seems natural, is that it feels like something that generative models should be able to help us with, right? Generative models, like the whole idea is that they're going to like place high likelihood on things that are seen and lower likelihood on things that are not seen. And so they seem like they should be able to help us, right, learn like which of these things are we should be less confident in. So the basic approach we're going to do here is, yeah, I'm just going to just skip straight to this. So the idea is that first we're going to use BART as our generative model, and we're basically going to try to edit examples in the training data set to create things, kind of take a random walk starting from the training examples and move them around a little so that there's a reasonable probability that you've like moved to a different label, but you don't want to move so far as to get like completely irrelevant to the training data. So the way this works is we're just going to kind of like randomly mask a phrase and then ask BART to fill it in, add some high temperature so we get diversity. And then we just like keep doing this a few times. And this, yeah, and basically we're going to throw these examples into the training data. So back up here, the pipeline is that we have this generated OD data that we train the model on basically this objective that says, I want you to become as close as possible to the uniform distribution over labels. So like if you have high confidence, push on a label, you want to lower it. If you have low confidence on a label, you want to increase it. And that's just going to be multitasked with just like the standard training on the original training data. Okay, so we can do that. This all sounds nice. I'm gonna, yeah, that sounds nice. It turns out that this naive thing is actually not that great. So we are doing the area under the accuracy coverage curve is kind of this overall metric. And so you can see we're basically at about the same as max prob, which is this baseline that we're building on. So that's not great. And if you look at these other two metrics, so AUROC is basically just saying how well can we distinguish examples we get right from examples we get wrong. And we're actually getting better at that. We're getting better at distinguishing the correct predictions from the wrong predictions. On the other hand, the model has gotten much worse just at like normal accuracy. And so that's, even if you're better at distinguishing correct from wrong, if you're wrong a lot more of the time, that's still bad overall. So yeah, so how do we address this problem? Basically, the analysis here is that like, well, we have we are able to generate some examples with our process that either are like of the held out class or some OD of some other class. There's some things that are kind of get edited very far, and so they're like more implausible examples, which are maybe not that helpful, but also not that bad. But then we also, turns out, have a lot of examples that are just like still in distribution, like we didn't edit them enough, or we didn't edit them in the right way. So like, and this is what seems to be causing us to have low accuracy, right? Because we're just telling the model to be unconfident in all these examples where there is actually a correct answer. Okay, so the fix here is to do what you might think of as like kind of self-training with outliers. So we're going to just train a normal classifier and then identify the low confidence examples based on that classifier. And then we're going to take those and basically train to say, hey, you should have even lower confidence on these examples. So this is kind of the reverse of self-training, where you normally like find high confidence predictions and you make yourself even more confident, right? It turns out this like reverse self-training thing also does quite a lot better. So when you add this filtering to the mix, we're now much better than MaxProb, and we're like competitive right now with this like kind of state-of-the-art contrastive learning based approach. And yeah, you can see that we're especially doing, basically we are no longer having this big drop in distribution accuracy, and we're also still doing very well in terms of this distinguishing correct from incorrect predictions. Okay, so that's kind of where this project is right now. There's still a lot of stuff that we want to do, that some of which is in progress. But I think it's kind of nice that we're seeing the like thing that these generative models like do in fact can help us generate data that helps the discriminative models. Yeah, so some other stuff that we're still working on. There's a lot of variation across data sets that turns out to be very relevant here, like how long your inputs, or like how many of the input words correlate with the label. That determines basically how likely you are to be able to change the label by just like doing this masking stuff. So maybe the solution is like, instead of just randomly masking stuff, we should do something more targeted, stuff like use integrated gradients or something, identify words that seem correlated with the label and edit those, or maybe something stupider like take n-grams that are correlated with the label and edit those. And also there's like being able to combine this with some base approach that is better compared to MaxProb. It's also on the table. But okay, yeah, I will end there, only 4 minutes over time, and happy to take any more questions. Yeah, thank you. Yeah.
Just a side note, when you showed the results from your contrast sets on your parser for the cover work,
Yes.
the parser accuracy went significantly down.
Yes, that's a good. Yeah, I'm glad you brought this up.
Confirms the intuition that the parser is like reverse engineering the grammar that we use to generate the synthetic utterances, and it's not really generalizing past that very well, right?
I don't. So I guess the way we were seeing. So okay. So yeah, just to. So what Matt was saying is that if you look at the far right columns here and for the contrast sets, like, yes, the semantic parser is actually like not really generating the right programs. Even when you paraphrase, it's like not generating the right programs. Sometimes any of the time. I think so I'm not sure what that says about, is it just reverse engine? Well, okay, so I think that the thing that's still positive about this, I think, is that like so the programs are like incorrect, but they're still pretty close. I mean, that's how you can still get execution accuracies to like not be terrible. Yeah, I think this is on the to-do list of like exactly doing the error analysis on like what are the deltas between the things that are generated and the actually correct programs.
Yeah, to me, like the parser is just way overfed to the synthetic grammar that was used to create the sentences. And maybe that's like, what parser did you actually use? You just trained it, you said it was
It's
T5?
trained T5.
T5 was trained just on that data?
Yeah.
Like, I wonder if you would like only train an adapter, like some way to make it not overfit to that, but like keep its
Oh, I see.
related
Yeah.
to the discussion we had earlier.
Right.
About, like, surely there's something more general inside of T5 that could get a non-zero parse accuracy on the paraphrase data.
Uh-huh.
How do you train the thing with the data that you have such that it doesn't lose that ability during expecting?
Yeah, it's a good question. So, okay, I guess maybe part of it is like when I say maybe I shouldn't have written paraphrase. It's so the paraphrase here is stuff like you change at least to like no less than. So there's some sort of like, I think it's not, I guess I've been arguing with Bill about this. Like, I guess I was saying that I'm actually not convinced that T5 like knows this off the bat because it's some sort of like logical equivalence rather than like a simple like lexical paraphrase. Yeah, but I don't know. Maybe I could be wrong.
And yeah, if you have if this is very narrow and like is only looking specifically at that exact paraphrase, then yeah, I could believe this more. But if it's like a broader set of paraphrases, I expect something better than this.
Right. Yeah. So these were specifically for just like these like quantifier phrases. So yeah, it is narrow in that sense. We've been trying to broaden it. Yeah.
All right. Any other questions? Let's stop here then. Yeah. Thanks a lot.
Okay. Thank you.